Okay, so here is how you construct your Penrose pseudo-inverse if you're given a singular value decomposition of A. So let's start with that. And let's write these matrices out like we did before. And now let me label the rows and columns of sigma so we can better see which one belongs to which. And this labeling of rows and columns again helps to see these rules here. So for example, if you input to your sigma a vector that has only components in the directions of vr+1 to vn, then these will hit all of these zeros and will return you a zero element, which perfectly corresponds to this formula here for the kernel of A. If you give it an arbitrary input, then it's clear that the output will only be supported on components belonging to U1 to UR because you have zeros down here. And that underlines that the image is just the span of U1 to UR. Okay, and then the rest is clear from here because the U's form an orthonormal basis, so the corresponding orthogonal complements are just the spans of the remaining basis vectors for the image and also for the kernel. And now just to get started with the formula for the pseudo-inverse, let's assume A is actually invertible, in which case it must be square and full rank. Then your sigma will be a square matrix. The singular values will run down the main diagonal, ending up in the opposite corner, and all of them will be non-zero because the rank equals the size of the matrix, which means sigma is invertible, and we can simply write down the inverse of A using this factorization here. And remember that the inverse of a product is just the product of the inverses, but in reversed order, where we use that V star is already the inverse of V and U star is the inverse of U. And of course we can write down explicitly the inverse of our diagonal matrix. So of course you just take the reciprocals of your entries on the main diagonal and then recall that this is square and full rank, because we're saying so here, because A is invertible. And now the general case, when A is not invertible, probably not even square. So clearly you cannot speak of the inverse matrix. All you can do is write down the Penrose pseudo-inverse. But the formula is pretty much like here, with the only exception that you cannot take the inverse of sigma because sigma is not invertible, not even square in general. So instead you take the Penrose pseudo-inverse of sigma. And now of course you have to say what that is. And here's the answer. Because the pseudo-inverse is going in the other direction from the second space back to the first space. So while the original matrix is M by N, the pseudo-inverse is N by M. And essentially the rows of U and V get exchanged. So you can see it here. Where there used to be U, there is now V, and where there was V, there is now U. Same here with the labels of our columns and rows. And the singular values that are non-zero get inverted, so you get their reciprocals. And the ones that are zero they simply stay at 0, so you just ignore them. There's of course no point in trying to invert them, and in fact it would not be right to try and invert them, and I want to try and explain that. And for that explanation, let's refer to these spaces up here, and maybe I should use different colors, not all blue. Okay, excellent. Now let's color the corresponding rows and columns of sigma, and also of the sigma plus more Penrose inverse. And now remember our 3-step description of the pseudo inverse, which we gave at first. And the first step was orthogonal projection onto the image of A, that is the red space. And you can see that here by the fact that we are ignoring everything that is coming from the orthogonal subspace or complement of the red space. So it's all 0 in here. And then this square block here is just the inverse of that square block here. And you can see that these two blocks are only playing between the red and the blue space, okay? So this one is going forward from the blue to the red space, so it's coming from the orthogonal complement of the kernel, which is in X in the first space, and it's going to the image of A, which is of course on the other side in Y. And now you have to go backwards, so starting from the image of A, where you have projected onto orthogonally by ignoring everything here, you want to go back to the blue space by exactly inverting what A was doing here. And obviously the inverse of that diagonal matrix is just diagonal matrix of the inverses of the reciprocals of these numbers. And then if you do that, and if you put zeros down here, and here you have zeros anyway, you already make sure that your result will stay in the blue space. So you're not going to use the black space. And what is the blue space? The blue space is the orthogonal complement of the kernel. And that was our last step. So the last step was orthogonal projection onto that blue space here. And we are doing this by ignoring everything down here. Okay, so I mean, of course, this is a bit hand-waving explanation, but I hope it helps to understand that this is the formula for the more Penrose pseudo-inverse in terms of singular value decomposition. So in particular, the product of 3 matrices that you get here is again the singular value decomposition, but now of A plus. So the numbers that you see on the main diagonal here are the singular values. And they are obviously just the reciprocals of the original singular values that are non-zero, and the zeros remain 0. Okay, very important message. We will deal with that over the next couple of lectures. One thing that I didn't say in this special case here of an invertible matrix A is that the inverse here is of course also the pseudo-inverse. So if the inverse exists, then that coincides with the more Penrose pseudo-inverse. But if not, then that's something different, of course, and here's the formula. Okay,